Hello, welcome to another lesson of sectoral structures theory. Today we will review the Meem function. We touched on it previously, but we want to focus more on it because it's a very important function in this theory. So the Meem function, we defined it earlier as the total number of possible sectoral structures of a given degree. And we said that we call this a complete sectoral set of degree n. So for example, if we get all the sectoral structures of degree 4, we call this a complete sectoral set of degree 4, st subscript n. And the size of this sectoral structure is defined by the Meem function. We saw the Meem is based on the Arabic letter Meem, and we called it Meem of n. It's very important for me to define this function because it will be very central in this framework. So let's quickly review. Let's look at a complete sectoral set of degree 4. That means we get all the sectoral structures of degree 4 as geometric entities. So each structure, whether we write it in standard form or in reverse form, it still counts as one sectoral structure. So in a way, we kind of preserve this, or we follow this symmetry. So let's look at the degree 4 sectoral structures. We have 6 of them. We've got the 4 subscript 4. We also said we call this type of structure a theta structure. So this is theta 4. Another way to think of it is the most compressed form of a degree 4 sectoral structure. Then we have 2 squared subscript 4, which is basically this form, 2 semicircles attached together. We notice here we have an alpha joint, a beta joint, and an alpha joint. It has an order of 2. The other sectoral structure of degree 4 and order 2 is this one here, and that can be written as 3, 1 subscript 4. Now let's look at the order 3. We've got 1, 2, 1 subscript 4, 2, 1 squared subscript 4. And finally, we have our xi structure, which is xi4, or 1 to the power of 4 subscript 4. So we have 6 possible sectoral structures of degree 4. Notice that if we reverse this, we get 1, 1, 2 subscript 4. That still counts as the same sectoral structure when we're doing the Meem function. And for this reason, if you review when we talked about free and bound actions or functions, this is a free function, meaning that each structure and its reverse count as the same entity. So we will say that the magnitude or the size of an ST4 set is, or sorry, this should be STN, is equal to Meem of n. Now let's try to figure out how to calculate Meem of n. The easiest way to do this, because the counting really becomes challenging when we're looking at structures that are symmetric, we're going to separate all the degree 4 sectoral structures into 2 groups. First, we will have the symmetric sectoral structures, which we've already talked about. And then we will look at the non-symmetric sectoral structures. The symmetric sectoral structures, we counted them previously using the omega of n function. The non-symmetric ones, we will count them as, or asymmetric, we will count them as z of n. So symmetric and asymmetric. We're going to divide them into 2 groups. Now, We've already figured out how to calculate the number of symmetric sectoral structures of degree n. We've defined this in the prior lessons, and we said omega of n depends on whether n is odd or even. And we can say overall it's equal to 2 to the power of n over 2, where we round n over 2 down. So if n is 4, 4 over 2 gives us 2. We're fine. If n is 5, we say 5 over 2 is 2.5. We round it down to 2. So this gives us the omega of n. Now let's try to figure out z of n. To do that, let's go back to the idea of looking at the joints within the structure. So a sectoral structure of degree n will have n minus 1 joints. Now, if we want to figure out the total possible sequences that we can get from this, so in this case, where we preserve or where we count reverse structures as unique sectoral structures, then T of n, or the total of n, is equal to 2 to the power of n minus 1, because we have n minus 1 joints and 2 possibilities for each joint. Now, Z of n will be the total number of structures minus the symmetric sectoral structures. So think about it. What do we have now? So we have every possible structure and its reverse. We removed the symmetric sectoral structures. We're left with every sectoral structure and, that is asymmetric, and its reverse. So we're left with twice the number that we're looking for. Therefore, we're going to divide by 2, and we're going to say z of n is equal to t of n minus omega n over 2. We already know t of n, so we're going to say z of n is 2 to the n minus 1 minus omega of n divided by 2. And this is as simple as we're going to get here for now. Now, let's go back to meem of n, or the total number of sectoral structures of degree n. We will say that we're going to add z of n, which we've already established, and omega of n. And this simplifies nicely to the following. Meem of n is equal to 2 to the power of n minus 1 plus omega of n divided by 2. Now, we've already said that omega of n is equal to 2 to the n over 2 rounded down. Therefore, meem of n will be equal to 2 to the n minus 2, which is just algebraic simplification. So 2 to the n minus 2 plus 2 to the n minus 2 over 2 rounded down. And this gives us the mean value for any given n. We have a few here to look at. So this is the degree of the sectoral structures, and this is the number. We have the first 6 here are 1, 2, 3, 6, 10, 20, 36, and so on. Let's look at another way to show this. We've seen that we can represent a sectoral structure in binary form as well. So just to keep in mind, for a degree n sectoral structure, we have a binary string of n minus 1. So 4, 4 would be 0, 0, 0. 1 to the 4 subscript 4 would be 1, 1, 1. And then every other sectoral structure will fit within this sequence. So here, while we're actually trying to count the total number of unique sectoral structures of degree n, we also get the total binary strings under reverse symmetry of degree or of sequence length n minus 1. So in this case, 0, 1, 1 and 1, 1, 0 are counted as one sequence. So we count the reverse as 1. We'll see many applications for this sequence, and it occurs in many places in mathematics and also in chemistry as well, especially organic chemistry. But it's really nice to also see that the same sequence occurs in the Meem function for sectoral structures. Thank you.